Today our goal is to design a lab procedure that will allow us to determine the muzzle velocity of our projectile launcher.
Well, before we start anything, we need a clear plan. We were told to use two angles that allow us to determine the muzzle velocity without using any trick.
And there are only two angles that work with that, 0 degrees and 90. So we'll start with those, and then we can design a third method for 60 degrees.
So if we launch a projectile straight up at 90 degrees, we can use the time it takes to reach the peak to find the initial velocity.
That's right. And at the peak of the motion, the vertical velocity is equal to 0, and its acceleration due to the acceleration of gravity is equal to negative 9.8 meters per second squared. We can use the equation Vf equals Vi plus At to solve for the muzzle velocity.
And to find the time to the peak, we'll measure the total time the projectile spends in the air and divide it by 2.
Oh, that's no good. Oh, that's better.
Next, if we launch horizontally at 0 degrees, the velocity of the projectile is entirely horizontal.
And since gravity is the only force acting on the projectile after it leaves the launcher, the horizontal velocity remains constant during the motion.
So, if we measure the horizontal distance traveled, we can use dx equals vx times t to determine the horizontal velocity. To find the time of flight, we'll use the height and the equation dy equals 1/2 gt squared because the initial vertical velocity is 0.
Finally, we need a procedure for determining the muzzle velocity using a 60-degree launch angle.
For this method, we can measure the total time of flight and the horizontal distance traveled.
With those measurements, we can determine the horizontal velocity using dx equals vxt. Since the horizontal velocity is related to the muzzle velocity by vx equals v cosine theta, we can solve for the muzzle velocity vx equals v cosine 60.
Once we have results from all three methods, we can compare them and analyze sources of error.
This gives us all three valid experimental approaches to determine the muzzle velocity. Now that the procedures are planned, we can move on to testing.
Okay, so for the last challenge, we're going to set the launcher angle 45 degrees and then use the average muzzle velocity we calculated in our other trials to predict where the projectile will land.
And even better, Mr. Manticapri said he'll sit at the exact spot we predict. So, if our calculations are correct, we will literally show him the physics.
I feel like this is either a moment of triumph or the beginning of a lawsuit.
Mr. Manticapri doesn't seem to be too afraid.
So if we're going to figure out where the projectile lands, we need to find dx, the horizontal displacement, right?
Yep, and since the horizontal velocity is constant, we can use the equation v equals v cosine theta times t equals dx.
Cool. Except, how are we supposed to find the time?
Since we know the muzzle velocity and the launch angle, we can calculate the initial vertical velocity.
Right, and since projectiles are symmetrical when launched and caught at the same height, the final vertical velocity will be equal in magnitude but opposite in sign. So we can use Vf equals Vi plus At.
Translation, gravity will tell us the time.
So once we solve for time using vertical motion equation, we plug that into dx equals v cosine 45 times t. And boom, predicted landing point.
And boom, possible teacher casualty.
Sounds like we have a plan. If this works, we'll be legends.
And if it doesn't,
we'll blame the rounding error.
Oh, perfect shot. You got me. Oh!
Action.
Thank you for watching our video on projectile motion. We are Sacred Heart Academy, and we show you the physics!